Okay, I want to start today with a little warm-up of what we learned last class, a review of section 2.1. Go ahead and write this equation in standard form. Again, that might mean vertex form to you. And state the vertex and intercepts. See how far you can get on your own. I'm going to fully complete the square and then I will update you. So pause the video and see if you're completing the square is correct. Okay, check you're completing the square. Hopefully you got the same answer as me. Now remember, once you've got it in vertex form, there are two things that should be easy to find. First, and hopefully it's obvious, the vertex should be easy to find. That is why up until now, we called this vertex form, but our book does call it standard form. The other one that's easy to find because we do have this in the other form is the y-intercept. See if you can name your vertex and your y-intercept. Constant in the equation at the very beginning, -7. But remember, on your answer blank, a y-intercept is a point. These are things you lose points, no pun intended, for on your pre-calculus test. So make sure you write your y-intercept as a point. That leaves us with trying to find the x-intercepts. You're welcome to do quadratic formula on that top equation, but I do think it's easier. That's one of the reasons we put it in this form. If we take our new standard form, set it equal to 0, because for x-intercepts, y equals 0. Start moving things to the other side, so add 39 over 2. Divide by 2. Remember, if it's already a fraction and you want to divide it, you multiply the bottom, in this case by 2, right? Because we're dividing by 2. I keep saying 2, so I wrote a 2. Then to get rid of the squared, square root both sides. Also remember, when you square root both sides, you get plus or minus the square root of 39 over 4. That is the same thing as plus or minus the square root of 39 over 2. I just want to point that out. I don't care how you write it, but if the square root goes to the ground, it's over 4. If you only put the square root on the top, because the square root of 4 is 2, you can write it as that other way. And then finally, minus the 5 halves. I like to put my 5 halves in front of the plus minus sign. So my x-intercepts, there are 2 of them. That's what the plus minus means. And they are also a point. I'm going to minus 5 halves, so -5 halves, plus or minus square root of 39 over 2, comma 0. Some of you might notice that they're both over 2, so you could also write it like this, which might look a little more familiar when you solve quadratic formula. Your answer ends up looking like that. So, warm up, and hopefully you guys understood most of that. Okay, here we go. Section 2.2 is polynomial functions of higher degree. This is, if you had integrated 3 with us at Whitney, this is where we left off last year during distance learning. So, polynomials, they look like crazy roller coaster things happening. They are still functions, so they do need to pass the vertical line test. My vertical lines can only cross once. You can't have something like this that like doubles back under itself. That is not a polynomial function because it doesn't pass the vertical line test. They're smooth continuous curves with no breaks, gaps, or sharp turns. Notice my polynomial example is curvy. It doesn't come to a point. It's not That is not a polynomial function. So make sure your graph has curves. The degree of a polynomial determines the end behavior of the graph and the number of direction changes. So direction change in my little example at the top. This is going up, that's one direction, and now it changes down. That's 2. Then it goes up again, that's 3. Then it kind of does this crazy thing here and then goes up again. So direction changes and it's minimum. Find the degree. So we need to know how to find the degree, sorry. In expanded form and in factored form. So I am going to write an example for each of these. So let's do expanded form in blue. So an example of an expanded form polynomial is f of x equals 5x to the 6th plus 4x to the 5th minus 7x squared plus 3. So notice when we talk about polynomials, we want the biggest exponent in front and we want the exponents to count down from there. You don't need to see every exponent, right? There's no x to the fourth in my polynomial example, but we do want to count from biggest to smallest, so we want to put it, that's in standard form. When we have a polynomial in expanded form, there are only plus and minuses in between the terms. There's no multiplication happening. And when it's in expanded form, the degree is the highest exponent you see. Let's see. Highest exponent in expanded form. So in my example, the highest exponent I see is a 6. The degree is 6. Factored form. A polynomial example in factored form, f of x might equal, let's make it g of x just so we don't think it's the same. G of x might equal 5x squared times x minus 1 cubed times x plus 7 cubed. That's a good example. So notice that they are in parentheses and, factored form. They are in parentheses and there's a bunch of exponents, right? All those little x's have exponents on it. It's the sum of the exponents of the factors. So only if there's an x, so this x in front has a 2, so I should keep that in mind, I've got 2. This x in the parentheses has a 3, so 3 more, and that x at the end has a 3, so the degree, if I add those exponents together, 2 plus 3 is 5, plus 3 more is 8. So you need to know how to find it in both forms, expanded and factored. I do really quickly want to make a little note at the sum of the exponents of the factors on x. It only counts if there's an exponent on x. Okay, so degree is going to be super helpful. I'll show you how it helps in a minute. The other thing we're going to need to know is leading coefficient. So the leading coefficient test, the leading coefficient determines the end behavior of the right tail. So if we know the degree and we know the leading coefficient of a polynomial, we know what way the right tail is going. And because we're going to combine it with degree, that means we're also going to know the left tail. So together, these give us our end behavior. Let's make a little note of that. Together, these two things give us our end behavior. The tails, the arrows. So leading coefficient test. If the leading coefficient is negative, then the right tail goes down. If the leading coefficient is positive, then the right tail goes up. So leading coefficient, by the way, the number in the very, very front, only if it's written in descending order. So in my expanded form up above, 5x to the 6th, x to the 6th was my biggest exponent, so the 5 would be the leading coefficient. In my factored form down below, it's a coincidence by the way, the 5 in the very, very front would be my leading coefficient of that example. So we are going to make a little table to help us with this. That's why I have so much room here. We are going to put this information together into a table. Maybe you won't need this table in the future, but it'll be in your notes so you have it. These two things tell us about our end behavior. So this is our end behavior table. We like to know, is the degree an even number or is the degree an odd number? Then we also like to know, is the leading coefficient a positive number or is the leading coefficient a negative number? So what we're going to draw in these boxes is what the end behavior, what the arrows would look like. I'm going to do this a little differently, so bear with me. When you think of an even function, a function that has an even exponent, what's the smallest even number you know? Positive even number. So the smallest positive even number you know is 2. So if you just think to yourself, this is my little thought bubble. If I think about x squared when I'm doing even polynomials, that will help me figure out the arrows. So imagine a graph of x squared. if the leading coefficient is positive, so if you have a positive, x squared is a parabola, right? A positive parabola looks like this in general, right? The two arrows go up and then there's a vertex at the bottom. But we are just doing end behavior. So we get rid of the middle, and that would be my end behavior. The left arrow is up and the right arrow is up. What about a negative parabola, right? I'm still in the even column. So I'm still thinking about a parabola. Maybe I draw the negative parabola first, the whole thing. But because I'm not doing a parabola, I'm doing a polynomial, I erase the middle. A negative even polynomial, both arrows go down. What about odd? What's the smallest odd number you know? What are you going to think about? Thought bubble. I'm going to think about just x. Y equals x. Y equals x is just the equation of a line. A positive line goes uphill. But I'm not drawing lines, I'm drawing polynomials. So I erase the middle. And now I know a positive odd polynomial. The left arrow is going down and the right arrow is going up. What about a negative line? Negative lines go downhill. But I'm not just graphing lines, so I erase the middle. For a negative odd polynomial, the left arrow goes up and the right arrow goes down. We're going to fill in the roller coaster in the middle later, right? It does a bunch of crazy stuff. But now we know what our arrows do. Okay, so now we have the beginning and the end of our polynomial. How do we fill in the middle? Well, we fill in the middle with the zeros. The zeros are all the values where p of x equals 0. So these are called zeros. These can also be called roots. These are also technically the x-intercepts. So I need you to understand all three of those represent the zeros, but x-intercepts would be written as x comma 0, whereas a 0 is just written as x equals, I'm going to call it a. I should probably call this one a also. A comma 0. But notice the a is the same no matter what. So once you know the 0, and it's just a simple zero product property, we'll do an example in a minute. The multiplicity tells you what it looks like. So the 0 is going to tell me where my point is. Maybe I have a point right here. The 0 gives me the point. The multiplicity tells me what it's going to look like right there. So multiplicity is just a fancy term for the exponent. You look at the exponent that is on your factor to figure out what it looks like. So for example, a single root. If your exponent is x minus a, and if there's no number there, there's an imaginary 1, right? That's called a single root, and it goes through the x-axis. So if it was my red dot below, it would go straight through. It might be going up, or it might be going down, straight through, but I do know it would go straight through the axis. A single root acts just like a line. It's straight. Then, let me erase my example down here. What if it was quantity x minus a and it was squared? So now my exponent is a 2. So I would say it has a multiplicity of 2, or a double root. The multiplicity is literally the exponent. I see a 2, it has a multiplicity of 2. That one's going to bounce off the x-axis right at the root. So another way to say this is that it's a vertex, or that it's a parabola. Different people say different things. But so if that, let's just say a was here again, there's my point. At a, x equals a, it's going to bounce right off that dot and go back the way it came from. Or it's going to bounce right off that dot and go back the way it came from down below. Either way, notice it doesn't go through the axis any other place. It bounces. It's the vertex I'll draw both at the same time just so you see it. One of those is what it's going to look like. Finally, we only go up to the third power in this class, x minus a cubed. If I see an exponent of 3, I know it's a triple root, or it has a multiplicity of 3. It's going to have an inflection point, because if you think of something that's cubed, you think of a cubic, or an inflection point. I didn't mention it up above, but if I think of something that's squared, I think of a parabola. If I think of something that's just x minus a, I think of a line. So these should all kind of make sense. So if that's my dot down below, it might come up, try to draw an inflection point and go the other way. Or it might come down, try to draw, that one's not very good, try to draw an inflection point and go the other way. So triple root x minus a cubed. So now we're going to put it all together and finally sketch a polynomial. Okay, so this one's kind of done for us, just to get the general idea. They gave us a polynomial in factored form. By the way, without a calculator, I can only graph polynomials if they're in factored form. So there it is. Let's talk about how they got these answers. They say the degree is 4. So if I look at my exponents, because this is in factored form, sum of the exponents, I see a 2 there, but that's the only number I see. But I do see an x here and an x here. They have imaginary exponents of 1. Notice the 2, negative 2, in the very front does not have an x. So it does not count in my degree. So 1 plus 2 plus 1 is how they got degree of 4. And behavior, notice how we answer this question. I'm going to give you another way to answer it in a second. But since the leading coefficient is negative 2, so negative, and the degree is 4, so even, negative even, remember negative parabolas, the arrows are down, down, and that is the other way I accept you to answer it. Instead of writing both tails down, you could literally draw me 2 arrows down, but I need to know which one's the left and which one's the right. Okay, now we know what the arrows look like. Next, we need to find the zeros. Zeros is x-intercepts, so zero product property. Set the equation equal to 0. You take each factor one at a time and do zero product property. Only if they have an x in it. X plus 3 equals 0 gives me negative 3 as the root. X minus 1 equals 0 gives me 1. But because it has an exponent of 2, you have to tell me with multiplicity 2. X minus 5 equals 0 gives me a 0 of x equals 5. So notice if there's an exponent bigger than 1, you have to say with multiplicity. You're welcome to say with multiplicity 1 on these ones, but you don't have to. But 2 or more, you do have to tell me the multiplicity. These are points on your test. Finally, y-intercept. Plug in 0 for x and they got the y-intercept. So let's put this all together and get a sketch. So we need an x and y-axis. The y-axis will not be to scale. I mean, look at the y-intercept. The y-intercept is all the way up at 30. The graph I just drew, 1, 2, 3, 4, 5, only goes up to like 6. So it's crazy to try to draw how high these go. So this will just be a sketch, but what's happening at the x-axis is very precise, and that is what we're grading you on. So to start graphing it, you start with your zeros. So I have a 0 or a root over here. These are I'm doing that one in green, at negative 3. So the x-axis is to scale, so use your graph paper, negative 3. I have another one at 1 on the x-axis, use your grid, and another one at 5. These are my roots or zeros or x-intercepts. Now I'm going to use my knowledge about the tails. So my graph crosses at this green dot on the left. It does not cross the x-axis ever again, only on the left at the green dot. So I can draw my left arrow. I'm using this right here. My left arrow must be down, so I can draw it down there. And then it only goes to the right to the light purple arrow. So my right arrow must be down over here. And now I'm going to fill in the middle. You cannot touch the x-axis anywhere other than those 3 dots we graphed. So x equals -3, right? It's unfortunate that these are in order, but they won't always be in order. So the green dot is x equals -3. If I look over here at my notes, it has a multiplicity of 1. What does a multiplicity of 1 act like? It acts like a line. So I'm going to go straight through my green dot. Somewhere up here, it gently curves and comes back because it has to go through your other dots. That's a sketch. You might go up this far and turn it around. Or you might go up this far and turn it around. But curve it gently and turn it back around because it has to go through that orange dot. That orange dot is at 1. Over here, it says that it has a multiplicity of 2 because the exponent was 2. What does a multiplicity of 2 act like? It acts like a parabola or a vertex. So it's going to touch the orange dot and then go back the way it came from. That's the vertex of a little parabola right there. Then somewhere up here it turns around because it still has another root to go through. That root has a multiplicity of 1, so it's going to go straight through. And I landed on my arrow, so I probably did it right. Let me show you really quick what students tend to do that is wrong, so don't do this. But I get a lot of students who do this. Let me use a highlighter and then I'll get rid of it. And they go, oh, straight through, and then bounce, and then come back through, and then straight up. Well, right here, you cross the x-axis at a spot that is not supposed to exist. So make sure you only cross your x-axis at the points that we plotted in the beginning. Okay, this is other information about that same graph, so the one we did over here, that you can find using your graphing calculator. I can't teach this to you on the computer, so either your teacher's going to go over it in class or we're not going to test you on it. So if it's something we do in class, make sure you understand how to do it. Here's an example problem. You can test out your calculator with it, but I can't go over this with you right now. Okay. So let's put this all together and graph this function. First thing you should notice is that this function is not in factored form. We only know how to graph something if it is in factored form. So we are going to want to factor this ourselves. So when I see f of x, I see that, first of all, it starts with a negative. I never like things to start with a negative, so I'm going to factor the negative out. And I see that both terms have at least an x squared in them, so let's factor that out. When I factor out negative x squared, now I have positive x squared. I'm factoring out a negative, so now I have -4. Well, that is still factorable. Negative x squared, that is a difference of squareds. X plus 2, x minus 2. Okay, so I factored it with you. See if you can find these things for me. See if you can find the degree, the leading coefficient, the end behavior, and the zeros or roots. Actually, I want to do x-intercepts also because I want to make a point about how we name those things. See how many of those you can find now that it's in factored form. Okay, so if you look at it in standard form up above, biggest exponent you see is a 4. Or if you look at it in our factored form, squared, imaginary 1, added together gives us 4. So you should have gotten degree of 4. Leading coefficient is -1. So, important parts for myself, degree is an even number. This is just for myself. And leading coefficient is negative. Negative even, negative parabolas, end behavior, down, down. Okay, zeros, zero product property. We have x squared in the very front, negative x squared. If you set x squared equal to 0, you're going to get a 0 of x equals 0 with multiplicity of 2. This is how we answer blanks that ask for zeros. X equals, and we include the multiplicity if it's bigger than 1. My next factor, x plus 2, if I do zero product property on that, is going to give me an answer of -2. And it's fine if you just include your x equals line with a comma, so I don't need to say it again. My last factor, x minus 2, if I do zero product property on that, I'm going to get a 0 of 2. Multiplicities of 1 do not need to be listed out. Now, x-intercepts. It's kind of the same question, but you answer it differently. Notation is different. The first 0, 0, comma, 0. The next one, -2, comma, 0. And the final one, 2, comma, 0. So I'm trying to make the point that intercepts are a point and zeros are x equals answers. Okay, now that we have all that stuff, we're going to put it all together and sketch this. So y-axis is never to scale. They get really, really tall really quickly. X-axis does need a scale. So it goes from 0, +2, -2. So 1, 2, 1, 2. First thing you do is plot your zeros. 0 is right at the origin. -2 and +2. Those are the only 3 places your graph can cross the x-axis. Now the arrows. Left of the final left dot, which happens to be green, is down. Right of the final right dot, which happens to be orange, is down. Now I fill it in. We work from left to right, just like we read from left to right. So the first point I'm going to hit is the green one, which is -2. It has a multiplicity of 1, so I just go straight through it. Somewhere up there I turn around because I have to go through the other dot. The next dot I'm approaching happens to be blue. That is 0. It says multiplicity of 2, so that needs to look like a parabola. Bounce right off of it. Somewhere up there I turn around. The orange dot, x equals 2, multiplicity of 1, so straight through, and I landed on my arrow, so I probably got it right. Okay, now we are going to work on going backwards. So write a polynomial function of least degree. Least degree just means don't add any extra x's to the problem that we didn't actually tell you. With integral coefficients. Integral coefficients means whole numbers, no fractions, no decimals, in expanded form, so that means I'm going to have to multiply it out, given the following zeros. So we have a 0 of 0, -5, and 2 plus √7. We want to turn those into factors. So 0 product property with what gives me an answer of 0? Well, that's just x by itself. As a factor, x what would give me a 0 of -5? Well, it's opposite, so it must be +5. As a factor, same idea, x opposite, so -2 minus √7. And then actually, we're going to talk about this another day. This might be a misplaced question. But anytime we give you an imaginary or an irrational 0, like 2 plus √7, you need to know that it comes with a conjugate 2 minus √7. The only way to get an irrational solution like that is, for example, to do quadratic formula. And when you solve quadratic formula, it's always plus or minus. So you're going to have to remember that x still -2, but plus √7 is also a factor. So what I need to do right now is I need to take, my answer basically is going to be f of x equals x times x plus 5 times x minus 2 minus √7 times x minus 2 plus √7. But this is in factored form, and it clearly says expanded form. So we need to take the time to multiply this out. My suggestion is to always multiply these complex conjugates together first. Sorry, not complex conjugates, just conjugates. One with a plus, one with a minus. When you multiply those together, nice things will happen. So maybe you need to make an area diagram. I always do. So let's make a 3, but that's not a square. Make a 3 by 3 area diagram for our conjugates. Something nice happens when you multiply conjugates. So one of them is going to say x minus 2 minus root 7. The other is going to say x still minus 2 plus root 7. Take a second and multiply those out. So check the inside and make sure you multiply this out correctly. When you multiply conjugates, look, I've got x root 7 and negative x root 7. I've got negative 2 root 7 and positive 2 root 7. Those will always cancel out if you do it correctly. Also, I went ahead and did this last box. Make sure you understand that root 7 times negative root 7 is still negative, but the roots cross out and you just get 7. So combine like terms. These ones up above, so I'm going to bring down what we already had. Well, I'll do that in a second, actually. These ones here multiply out to be x squared minus 4x. I've got 4 minus 7, so minus 3. Those two I have in red, I can multiply those together pretty quickly, right? Just distribute the x. So those two are x squared plus 5x. You have one more area diagram to do. Multiply that out, and you will get your final function in expanded form, integral coefficients, least degree. So make one more area diagram. I'm not going to show my work, and see if you get what I get. Okay, after you multiply it out, hopefully you got the same thing as me. Another thing to remember, f of x, we wanted a polynomial function, so make sure you include the f of x notation in order to get full credit. Okay, here's another one of our famous word problems you need to be able to interpret and solve. Make sure you read through the problem so you know what's happening before we go along together. Okay, so it looks straightforward enough. I mean, they give us the answer to volume, right? Volume is supposed to equal this. We need to verify that. So volume, length times width times height. So let's get some measurements on this thing. So there's the folded version on the left. Sorry, the flat version on the left. And then it folds up to be the one on the right. What would this distance be? So that's the side where it's folded twice. That's this distance. Remember, the length of each fold is x. So this is 24 minus how many x's do we lose? We lose 4x. So this side is 24 minus 4x. Keep that idea in mind and figure out what this side would be, which is this side. So it starts as 24, and then how many measurements do we lose? We lose 2 x's. And then finally, what is the height of this box? After you fold that all up, the height ends up being x. So for volume, in terms of x, volume equals length, so 24 minus 4x, times width, so 24 minus 2x, times height, so x. Cleaning that up a little bit, GCF, 24 and 4 divides into both of those. GCF, 24 and 2 divides into both of those. And then the final x. Multiplication, it doesn't matter what we multiply together first, so let's multiply those singletons together first. 8x. And then we'll multiply by the others. And now it looks just like the volume equation is supposed to look. Finally, domain. Domain is all the possible x values. But possible in this situation. So remember, in this situation, x represents a length, or a height if you want to be extra specific, but x is a length. So what's the smallest x could be so that this open box actually exists? So if x was actually 0, would this be a box? Could you put anything in a box if it doesn't have a height whatsoever? You can't. So the domain needs to be a little bit bigger than 0. So 0 with the parenthesis. So 0.1 would technically be a box. 0 wouldn't, but anything bigger. So we use a parenthesis to say it's not including 0. Comma. All the other edges need to exist also. So you've got 24 minus 2x. I could have made that purple. And then you've got the 24 minus 4x. I need all of these numbers to be bigger than 0. So you can solve both of them. 24 greater than 2x, 12 greater than x, or x is less than 12 if you like to write that a little more neatly. 24 greater than 6x. Oops, why did I change it to 6? 4x. Divide by 4 and you get 6 is greater than x, or x is less than 6. So theoretically, on this one, I could plug numbers all the way up to 12. But as soon as I hit 6 on this one, this edge is going to disappear. The 24 minus 4x edge is going to disappear. So I can't go any bigger than 6. And since I can't actually equal 6, I need a parenthesis.